Hello and welcome to day 20 of my Advent of Code series for 2020. If you've missed any of the previous episodes, you want to check those out, check out the playlist linked right up there, and be sure to get subscribed to me so you don't miss any of my future videos. So today we're tackling day 20 called Jurassic Jigsaw. So the idea here is that the elves are still worried about this sea creature, so they've sent us a satellite image, but the problem is that what the thing sends us is just a bunch of different tiles from the satellite's camera array, and also every single one of those tiles is randomly rotated and flipped. So the way that we line it up is that the borders of every single tile will match up with each other. So if you see here down in this example, right here, so you'll see this column right here is equal to this column right here, this row right here is equal to this row right here, and so on and so on, and that is how we fit the tiles together. So for the first, we have to go ahead and report back the ideas of the tiles that end up in the corners once we have assembled our image correctly. So I recommend you go ahead and give this a try, and then we'll jump into my code right about now. So first thing I do is I read in our tiles, and what I'm doing here is I am reading them into a dictionary where I am mapping the tile ID to the actual tiles, and then we're just returning that as our tiles. So then I have some utility functions here, which we'll go over. First then is get borders, so this just returns a tuple containing all of the different borders, doing the top border, and then the right border, and then the bottom, and then the left. And then get flips returns all of the different ways we can mirror it. So that's going to be it by itself, and then it but reversed, and then every single line in it reversed, and then every single line in it reversed. Every single line reversed in it reversed, sorry. And then finally we have our get rotations. So this is going to give us all of our different rotations. So I start by just putting it in blank, and then we are going to go ahead and use this code to rotate it 90 degrees and push each version of it rotated 90 degrees back into here. And finally we put that all together with get transformations. So what get transformations is going to do is it's going to make a list. It's going to go through all the different ways we can flip it, and it's going to get all the ways we can rotate each of those flips, and then we're going to go ahead and put them into an output here, essentially kind of making a set, except for we can't hash lists, so we can't actually put them in a set. So on each one of them, I just check if it's already in the list, and if not, then I go ahead and put it in the list. So that is it for our sort of utilities up here, and then we can jump into our actual code. So we're going to skip over this monstrosity for now so that we can do it from the bottom up. So what we are going to go ahead and do is I'm actually using this getTiled function, which I only want to run once because of some weirdness with how it works. So this is actually getting called in the main function, and then the result of this function is getting passed into part one. So part one you'll see is returning all the corners. So let's go ahead and break down this function. So the first thing this goes ahead and do is it creates a dictionary called tile opts. So this is all of the different options that we have for different tiles. So this goes ahead and just creates a mapping of the ID to the list of the different like permutations or different transformations we can have of this tile for every tile that we read in. And then I go one step further and I create a dictionary that's going to convert every one of those options one step further into its borders, because it's really useful to have its borders, and we don't want to continuously call that get borders function if we don't have to. So what we do here is we iterate through our tile opts, and we go ahead and we just enumerate that list of tiles so that we're turning that into essentially a dictionary of its own. And what we do is, first of all, if we haven't already hit this in the dictionary, this is essentially just mimicking the way that the collection's default dict works, and we're setting it to be a second level dictionary essentially. And what we're doing is we're mapping the tile of that ID, of that transformation ID, to be its borders. Then the next thing that we do once we've built up our tile border opts array is we find the actual dimension that we need for the board. So that's just going to be the square root of the length of the tile opts, because it's supposed to be a square in the end, and I use I square root just so that I don't have to round it after, and it just gives me the integer right off the bat. And then what I do is I build this base tiled array, which is just going to be an array of the correct dimensions for what we need to our fully put together grid to look like in the end, except for I fill them all with nuns. I just do this because we need a sort of base case for our actual recursive function that we use to actually do the tiling. And then we return tile ops, which is needed for part 2, and the actual result of this recursive function here. So we can now jump into this actual recursive function right here. So this takes in a tiled, which is our result essentially, tile ops, which is all of the different permutations. This is actually taking in the tile border ops from this function here, but I don't want to keep typing that over and over again. And then we take in the dimension. So the way that we do this, and we also initialize x and y to 0 on the first call, and we have a set called scene that is initialized as an empty set on the first call. So what we do is if y is equal to dimension, so that means that we have iterated through every single thing, right? Because if y equals dimension, that means we're out of the bounds of the list. We've gone through every row already, so then we just go ahead and return tiled. That means we've hit our sort of base case there. If we've run through everything and we've built the array as we need. So then what we go ahead and do is we get our next x and our next y, and then I just do the sanitization here, which is just to say if we've gone out of bounds of the x in the next x, then we just go ahead and roll that over to go on to the next row, since y is our rows and x is our columns. Then what I do is I loop through our tile options. I get the ID of that tile. If it's not already in scene, if it's already in scene, it means we've already placed it in the grid, so we just go ahead and skip it. I did this so that we could avoid actually mutating the tile ops thing right here. And then if not, we go ahead and add it to scene. Then what we do is we go ahead and go through every single permutation of it. So this is every single way it could be transformed. And I grab the top and left of it because I want to go ahead and see if it fits into the array at the specific point. There might be a better way to do this. I'm not sure if you maybe get all of the valid neighbors for something at each point, but it's 3:30 a.m. and I'm not going to iterate on this anymore. So then what we go ahead and do is if x is greater than 0, so this means if this is not the first thing in the row, then we go ahead and check to make sure that the tile to the left of it is actually going to fit with it. So what we do there is we go ahead and get the neighbor, which is going to be whatever is already in the array, but to the left, already in our tiled array, but to the left. We get its right-hand column and we make sure that it equals our left-hand column. If it doesn't, then we go ahead and skip this and we move on to the next possible thing in the array because we know that this doesn't fit here. So then we do the same thing with y. So unless y is 0, which means we're at the top, then we go ahead and make sure that the bottom of the thing above us fits with this. And if not, then we go ahead and skip this option. So then what we go ahead and do is we add it into our tiled array, and we go ahead and make this call with our new mutated data to go ahead and see if we can actually build an array on this point. So then what we go ahead and do is we go ahead and say if answer. So once this resolves fully, that means once we get to a base case, which is either going to be this base case up here, which is a success, or it could be this base case down here, which is a failure. So if it's not none, then we go ahead and return our answer, and that is it for that. So then at the end of that, we remove ID, because if we haven't returned in here, then that means that this was an invalid path. So the previous answer before this is no good. So we can go ahead and take it out of our scene set. So then what we go ahead and do is we set that location back to none, and we return none, which means that this is going to get caught in the next level up here, and it's going to say this answer is no good, and it's going to go up and try the next neighbor, and so on and so forth until it finds something that works. So once that finishes running, we will eventually get our fully correct tiles here, and our getTiled function will go ahead and return that. So then for part 1, we can just go ahead and multiply together all of the IDs of the things in the corner here, and that is going to give us our actual answer for part 1. So once we're done with that, we can jump into part 2. So for part 2, we need to actually check this image for sea monsters. So the first thing that we have to do is the borders of each tile are not actually part of the image, they're just there for the alignment part, so we can go ahead and remove them. So we remove the borders of each tile, and we can push them together to form one grid. And then we have to search for our actual monster, which fits this pattern right here exactly. So then the spaces in this pattern can be anything, either a block or a dot, it doesn't matter. This is still a sea monster. And we have to remember that this grid right here may not be flipped or mutated itself to be in the correct orientation, so we need to check all of those. So we have to make sure that we go ahead and flip it into the correct orientation, and then we can see here how many sea monsters there are. So we need to go ahead and say how many of the pound signs here are not part of a sea monster in our input. So I recommend you go ahead and give this a try, and then we'll jump into my code. So here for part 2, the first thing that we did is we go ahead and remove the guides. So how I'm doing that is I'm essentially building up our end grid here by looping through our tiles in tiled. So this is going to get tiled from our get tiled function up here, which if you remember builds our actual grid, but that grid is actually just a bunch of the indices of what tile in what orientation go at what spot. So we're going to essentially just dereference those, get rid of the borders, and then add those into our out grid right here. And then eventually this will get us a grid that holds all of the actual tiles that we need in our finished picture. So this is essentially going to give us our finished stitched together satellite picture, which still may need to be flipped or rotated. So then I just defined as a constant our actual monster pattern here, just as a string, so that I could go ahead and parse through that. And then I wrote this little parse monster helper function. So this is going to actually break down this string into the data that's useful from it. Specifically, monster locks is going to give us all of the locations that have a pound sign. And then also, as I was writing the function, I noticed it would be super useful if I had the maximum x value at which a pound sign occurs relative to the top corner, and the maximum y value relative to the top corner that it occurs, just because that would make it really easy, and I could go ahead and have my loop without having to use try catches in the next thing, which is our check monsters function. So what this does is this reads in our data about our monster from our parse monster function, and then we go ahead and create a set called monster spots. So what this set is going to hold is all of the pound signs in our grid that do belong to monsters. So now what we're going through here is we are looping through our grid. First, I am checking to make sure that a monster can fit in this part of the grid right here. So I'm saying if y plus max y, so max y is the maximum y offset at which a pound sign in our monster occurs. If that's greater than the length of grid, then we know that a monster definitely can't fit here because it doesn't have enough room. So we can go ahead and just break out of this loop completely because we've gotten to the end of that. And then in our x, we do the same check, but with the max x, and we check the other dimension of the grid to make sure that we're not past it. And if so, we can stop looping through x's because that means that we're done with that area. So then I initialize a thing called isMonster, and I initialize that as true. And then what we go ahead and do is we check all of the offsets in our monster locations thing that we got from our parse monster. We go ahead and add all of those offsets into the indices that we're checking right now. And if though there is not a pound sign there, which is what we expect if there is a monster, then we can set isMonster to false and stop checking this location. And then at the end of that, if isMonster is still true, then what we can go ahead and do is we can just add all of those actual locations. So those are going to be the points in our grid where we have a pound sign that is from a monster. We can go ahead and add that into our monster spots array. So we'll go ahead, loop through the entire grid and do all of that. And then if the length of monster spots is 0, then we go ahead and return none. And what this is going to mean is that this grid is not in the correct orientation. So either it still needs to be rotated or flipped. But if that's not the case, then what I go ahead and do is I create a thing called all filled. I go ahead and just loop through the entire grid, check for all of the pound signs in the grid, and add in all of those spots. And then I just subtract these two sets, which are both going to have our coordinate pairs. So that's going to get rid of all the ones that occur in both things and return the length of that. And that is going to give us how many pound signs do not belong to monsters in our grid. So then you can see for my actual part 2, what I'm doing is I'm getting our grid by removing all of the guides, so that's all the borders, and then we are going ahead and getting all of the different possible orientations this grid can actually go in using our getTransforms function from earlier. So that's going to do all of our flips and all of our rotation possibilities. We loop through all of those, and if the answer that we get from checkMonster for that grid is not none, so that means at least one monster occurs, then we go ahead and return the answer that we get there, and that is it for part 2. So today was essentially rule following, but I thought it was a pretty fun problem. That's going to be it for me today. I hope you enjoyed. Be sure to get subscribed to me and turn on post notifications so you don't miss any future videos, and I will see you next time. Goodbye.